Okay, hello. I am going to go through some chemistry review. Are you ready? This is our measurement unit, so unit 1. So the value of a measurement, like 42, is a number, okay? And then the scale of a measurement, like grams, for example, is the unit. So you need both in your answer. Every number you write down needs a number, a value, and a unit, a scale. So no naked numbers, numbers with units, numbers with units, numbers with units, numbers with units, no naked numbers. And remember, when you're doing percent error, the unit is percent. You cannot write just 23 or 17.41. You need a percent when you're doing percent error. These are some base units, right? But remember, you do not have to memorize these as they are on table D in your reference table. Okay. Also, that was a staircase, but we'll talk about that again. So units are found on table D, looks like this. Prefixes are found on table C, looks like this. And we can use the prefixes to build the staircase. Okay. Now, another important concept is accuracy and precision. Accuracy literally means like the right answer. So how close are your measurements to the right answer? The can says 753 grams. If your results are accurate, you got 753 grams or close to it. Precision is how close your measurements are to each other. So the can says 753 grams, but you on your balance get 702 grams, 701 grams, 703 grams, 702 grams. So your results are not accurate. Okay, they are not the right answer, but they keep repeating. All right, so accuracy is the right answer. Precision is repeatable. Accuracy, the right answer. Precision, repeatable. Doesn't have to be the right answer. Ideally, your results are both accurate and precise. So precision means precise. All right, so for certain and uncertain digits. In a measurement, there is always one uncertain digit. It's the last one. So let's look at measuring this eraser using the ruler. Okay, so sometimes it helps to draw a line from the edge, okay, or use something to indicate where it is. So especially on this screen, it helps to draw a line at the edge so I can exactly see where it is. So I'm going to zoom in a little bit so you can see. Now, looking at the big one, I can see there's 3, the big line, then 3.1, 3.2. So when I look at my zoomed in, I can see it is between 3.2 and 3.3. I have to guess because 3.2 is exactly what the ruler says. 3.3 is exactly what the ruler says. I have to estimate one more than my tool gives me. So I could say 3.23, 3.24, 3.25, what you think it is. And that last digit is the uncertain digit, okay? So converting kilograms to decigrams. So remember, this is the staircase, right? Okay, and we used table D to help us build it. We remember base units in the middle. Kilo, since its factor is 10 to the 3, is 3 steps up from the base unit. Deci's factor is 10 to the negative 1, so it is 1 step down from the base unit. Centi is 10 to the negative 2 as a factor, so it is 2 steps down from the base unit. And milli has 10 to the negative 3 as its factor, so it is 3 steps down from the base unit. And there you can fill in the staircase. Now, hecto and deca, you don't need to know those prefix names. You just need to know that those steps have to be held in place for kilo to be in the right spot. Okay, so when I do the conversion from kilograms to decigrams, I go 4 places to the right, and the decimal moves 4 places to the right. Okay. When you run out of decimal places, you add zeros, okay? And I'm not going to add a decimal point at the end of that number after the conversion because it would change significant figures. Okay, so conversion factors, they represent two equal units. So we can use dimensional analysis to do conversions, and we can do them with ones that use the staircase, but we have to do it for ones that don't. So I know that 1 kilogram equals 1,000 grams. So I can write it as 1 kilogram over 1,000 grams or 1,000 grams over 1 kilogram. The same thing for 1 hour equals 60 minutes. I can write 1 hour over 60 minutes or 60 minutes over 1 hour. I'm just hiding that one. All right, dimensional analysis examples. All right, so here's the first one. So you can see I set up 783.5 grams over 1. I use the conversion factor, and I need grams on the bottom because they have to be able to cross out like that, okay? And then, since grams are crossed out, I'm left with the units of kilograms, which is exactly what I want, okay? So then my answer is going to be 0.7835 kilograms. Now, if you look at the dimensional analysis for minutes to hours, I use a different conversion factor to convert minutes into hours, but minutes still cancels out, and I'm left with the answer of 2.92 hours, okay? Significant figures. Remember, 1 through 9, those digits are always significant. What about zeros? If there's a decimal point, then zeros at the end or right of the number are always significant, but leading zeros to the left, so ones before there's a 1 through 9, they're not significant. If there isn't a decimal point, then zeros at the end of the number are not significant. Remember, zeros in a sandwich, okay? If there's somewhere on either side of them a number that is a digit that is a 1 through 9, they're going to be significant. So let's check. The first one, well, that would be 3 significant figures because there's no decimal point. So those zeros, so let me show you. So these zeros right here are not significant because there's no decimal point. If there were a decimal point, imagine right there, then that would make those zeros significant. In this next example, I ignore this, which just converts the number into scientific notation. So I ignore this and I just look over here. So that means I have 3 significant figures. There is a decimal point, so zeros after the decimal point are always significant. This number, there is a decimal point, so it would be 5. These zeros count, they're after the decimal point. All right, let's look here. That's a lot of zeros here. There is a decimal point, so that means these zeros in the front are not significant, but the 0 at the end, it is. So 1, 2, 3, 4. This, there is a decimal point, so those zeros are significant. This one, no decimal point. This 0, not significant, so that one is 3. Okay? So remember, when we round, you should know rounding rules, right? So if it's 5 or greater, round it up. If it's less than 5, leave it alone. Don't round it up. Leave the digit as it is. Okay, so if I want to round this to 3 significant figures, first, second, third significant figure, I look over here. Oh, a 7 tells me I should round it up, so it should be 5, 6, 9. This one to 2 significant figures. Ignore, not significant, ignore, ignore. Oh, finally a significant figure. 6, 5, that's 2. Look over here. Oh, I should not round it up. Look at this one to 2 significant figures. 1, 2. Okay, now I have all these extra numbers, but I want to stop here. Okay, but I'm going to need it to be 1, 3, 0, 0. That only has 2 significant figures. I can't just make it be 13, because otherwise we could make a trade. You could give me $1,329.67, and I could give you $13. Close enough. It's not, is it? It is not close enough. So those significant figures that you had to remove, you replace them with zeros, okay? How do we add and subtract? So remember, all that matters are the digits to the right of the decimal point. So you just got to add the numbers first. Don't do anything until after you add. Just add up the numbers and then look at how many digits are after the decimal. Your answer has to have the least number. So that has 3 after the decimal, 2 after the decimal, 1 after the decimal. So my answer can only have 1 after the decimal. Okay, here's a subtraction. Okay, why is it this? Because 3 after the decimal, 2 after the decimal, the lowest number is 2. So my answer can only have 2 after the decimal. All right, what about multiplying and dividing? My answer has to have the same number of significant figures as the least number. So what does that mean? Well, let's look. This has 3 significant figures, 5 significant figures. Okay, my answer can only have 3. 4 significant figures, 2 significant figures. Well, my answer can only have 2. That would be 14. All right, scientific notation. Set up in this format where A is a number at least 1, but smaller than 10, and B is an integer, so you can't have a decimal or a fraction. So the rules for scientific notation, remember, you look for the number of significant figures, move the decimal point, count how many places you move the decimal point, put an exponent. If you started with a big number, your exponent is positive. If you started with a small number, your exponent is negative. But also you could remember this. If the decimal is being moved to the left, the exponent is going up. If the decimal is moving to the right, the exponent is going down. So it's left up to you and it's right down the line. Left up to you, right down the line. So here's an example of converting numbers into scientific notation. This one right here, you just have to remember that if you don't move the decimal point, you add this for scientific notation, times 10 to the 0. 10 to the 0 is 1. It also means don't move the decimal point. Okay? And the reverse, taking the number out of scientific notation, positive exponents mean it was a big number, so the decimal goes this way. It should go to the right. Positive exponent here, right? I should be making a big number. So I move the decimal 6 places. Okay, what about adding and subtracting? I'll let you read the rules. I also gave them to you in your notes. Okay, so let's look at an example. So adding and subtracting, I have to have exponents that are the same. So see, this is times 10 to the 3 times 10 to the 3. Beautiful, I can add them. 10 to the negative 4, 10 to the negative 4. Beautiful, I can add them. But I'm not adding for both. I can subtract. So this one I can subtract, this one I can add. I can do either. So all I'm going to do is, this case, subtract those numbers in the front and then keep whatever times 10 to the whatever scientific notation was there. Okay, so subtract the numbers and then just put the times 10 to the 3 afterward. This case, I'm going to add the numbers and then I am going to just keep the scientific notation, just like that. All right, what about multiplying and dividing? Well, similarly, I'm just going to multiply and divide the numbers. So in this case, I'm going to multiply those two numbers. For multiplication, I'm going to add the exponents. Then I'm going to put it all together. For dividing, I'm going to divide the numbers, subtract the exponents, and then put it all together. So 6.12 times 10 to the 11. All right, so remember the density formula. You can set up the triangle like that. Density equals mass over volume. Remember, table T is where you find the formula, and you can find values for density on table S. Density formula. mass over volume, and you use that to set up the triangle, if the triangle helps you. So let's do an example. The mass of silicone is 3.54 grams. Calculate the volume. So volume equals mass over density. So I cover volume and I look, oh, mass over density. I look up the density of silicone in table S. Okay, it's grams per centimeter cubed. Remember, centimeters cubed is the same as a milliliter. So I set it up like mass on the top over density on the bottom. And then my answer can only have 3 significant figures, so I round it appropriately. And I have units. Remember, no naked numbers. So does changing the mass or volume of something affect its density? Meaning if I have a bitty piece of aluminum or a giant piece of aluminum, does its density change? No. Okay, think about it. Otherwise, table S wouldn't be a thing. Okay, because it'd be like, well, the density of aluminum is 2.70 sometimes, but not always. It doesn't say that. It says the density of aluminum is 2.70 always. 2.70 grams per centimeter cubed always. So 1 atom of sodium has the same density as 300 billion atoms of sodium. Okay, it doesn't matter. In table S, we have the density, and it doesn't say it depends on what you have. It just says it's the density. It doesn't say it depends how much it has. All right, percent error. So here's the formula. Where can you find it? On table T. Remember, measured is what you get in the lab. Now, you might not have measured it, but somebody did, so you're given data. And then accepted has to be given to you in the problem, or you could look it up in the reference table. So it's probably in table S. In percent error, sometimes the wording says should yield. That means it's telling you what the right answer should have been, what the right answer was. So that's accepted. And actual yield, that's what you actually did in the experiment. That is measured. So here's an example. Percent error formula. Put the numbers in the correct place. So what do? First, I subtract. Then I take that answer that I got from subtracting and divide it by 13.01. Then I multiply it times 100. Don't forget this part. Okay, so my answer is going to be negative 1.153%, or for our purposes, we can write it as a positive number. We can think of the absolute value. So it would be 1.153%. All right, so remember, CER, state your claim, 3 pieces of evidence to support your claim, and then reasoning. So basically like this, think about claim, reasoning. They're almost the same sentence. Chemistry is my favorite subject. That's my claim. So let's give some evidence. I love learning about chemicals. I find them so interesting. 1 piece of evidence. Well, it's another piece of evidence. Chemistry explains how the world around us works. 2nd piece of evidence. Everything we eat, everything we drink, even everything that's in us is a chemical. 3 pieces of evidence. Reasoning. Because of those reasons, chemistry is amazing. So claim and evidence, then reasoning. So claim and reasoning are a sandwich. The evidence in the middle, the claim and the reasoning should be almost the same, okay? The reasoning should just have a little bit tied to the evidence in the middle, or just restating it. So a claim and a reasoning sandwich with the evidence in the middle, okay? So if you have a calculator, bring it. That's another recommendation. Show your work for your calculation questions. That means just don't write an answer. Show us how you set it up, okay? And then we're going to review with a blue kit. So in class, that's what we're going to do. So good luck on test day. I know you got this.